Hello, welcome. This is Dr. Hisham Saeed. In this video, we'll see an example of a frame analysis. So we have here this frame. It's kind of mimicking or similar to the frames we see for stadium structures. So in like the, remember DE here is kind of the overhang roof. And then remember BF, it's a little steep here, but in reality it's where people sit. It's like the step kind of seatings where people sit and watch the games. So, and this frame is repeated multiple sections of the stadium, and that creates that structure, 3D structure in the stadium. So we need here to go over these three steps or requirements. So first we need to calculate the reactions at supports A and F. So we have here two supports, hinge supports, and we have four members, A, B, C, D, and then B, F, and C, E, and D. So we would like to analyze the structure as a whole and finding the reactions that are of the supports that are holding the structure. And then the next step, step B, will be dismembering the frame. And we learned that frames are dismembered, but trusses are cut. So that's what we learn in introductory concepts about frames and trusses. So here we need to dismember the frame and draw the free body diagram for every member we get out of this explosion, like we're exploding the frame here. And we need to draw all the forces and also the intermediate reactions at the joints. And then considering parts A and B, we'll try to find the as many unknowns that we reveal when we dismember the frame. So the first thing is we will draw the whole free body diagram, or the whole frame free body diagram. So analyzing the free body diagram as a complete rigid body, and we will analyze the support reactions here. So support A is hinge, so we have here two reactions, AX and AY. But when we look at support F, it is also a hinge, but I can take advantage of my knowledge of what we call two force members. So a two force member is a view from what you learned in previous video, is that it's a member that's hinged, meaning that at both ends of the member it's supported or linked by hinges, and it's not loaded along its length, so there is no force applied at any point between B and F. And we kind of ignore the weight of the member. It's kind of a cylinder member. So in this case it qualifies as a two-force member. So what happens when a member qualifies as a two-force member? The hinge end of the member, I don't replace or represent it by two reactions. I actually represent it by one unknown reaction with a known direction. So I'm representing here, instead of saying Fx and Fy, I represent it by force Fb, and it's along the line of the member Fb here. The direction I know, which is the same direction of the member Bf or Fb. So here I'm reducing my unknowns from two support reactions at A and two possible support hinge reactions at F to only three reactions total, two at A and one at F. So when I start now analyzing this equilibrium of this whole body here, I apply the three equilibrium equations because this is a 2D system. So I start here with, if I think about it, which one to apply first. If I do sum of forces in Y, I have two unknowns, Fb and Ay. I can't solve right away for one unknown. If I do the sum of forces in X, the first equation to apply is still the same. I will see Ax and then the X component of Fb. So the trick here is apply the sum of the moments, because once you apply it correctly around a point, then you will be able, if you do pick the right point, you will be able to eliminate the moment from as many unknowns as you can. You will end up with one unknown. which we did here. Some of the moments around F, we cancel the moment from FB because it goes through point F, and I'm left here with AY, the moment from AY. And you, of course, AX also goes through F, so I'm ending up with one unknown here, AY. So the moment of AY around F is happening because of the moment arm of 1 meter. And I need also to account for the other forces, so the loads I have here. One thing I didn't mention is I'm representing distributed load here, loads as resultant forces. So I'm representing them with and instead of drawing or analyzing each arrow of the distributed loads here, I'm analyzing them as their equivalent, using their equivalent resultant. So the uniformly distributed load of 2 kilonewton per meter on the roof or on the overhang here, I'm putting it in the middle, which is at point E, which is above point F, so it doesn't cause a moment around point F, so it doesn't show up in the sum of the moments equation. But the resultant of the triangular load, which kind of representative of the wind, you can say load or pressure on the structure, so it happens at 1/3 of the height measured from the base or the right triangle here. So it's 1 meter from above or 2 meters from the base. And the resultant here is half of 2 kilonewton meters over a distance of 3. So that will be 3 kilonewton. So 3 kilonewton times the distance, the moment arm around F, which is 3 meters. So you end up with AY equal to 6 kilonewton, but negative. So the negative here is important because it means that the direction I assumed for AY is incorrect. The value is correct if I did the calculations correct, but the negative here means that I have to reverse the assumed direction of AY. Instead of being going up or maybe like carrying the structure at point A, is actually now pulling the structure at point A down. So the support is pulling the structure down at point A, which makes sense if you think about it. The wind is trying to overturn the structure to the right, so now the point A support is trying to pull it downward. So once I get AY, now I'll be able to apply some forces in Y, and in this case I will have the Y component of FFB, and I will be able to get FFB here. And when I get FFB, I will be able to apply the sum of the forces in X to get the last unknown here, which is AX. So without even really dealing with dismembering, exploding, and doing any severe actions here, I was able to analyze the truss or the frame, as a structure, as a rigid body, as a whole, and solve for the unknowns that I have, the support reactions. So I analyzed external equilibrium of that frame. Now, that's amazing. That was done, that was possible because I was able to recognize that member BF is a two-force member. Now, the next requirement asks for dismembering the frame. So kind of I'm exploding, I'm kind of, I'm doing with a VR headset, I'm kind of, with my fingers exploding that frame. So now I have these 4 members. And I try to draw here the interaction or intermediate reactions in the joint. So I have a hinge joint D. So I'm representing dy dx because it's a hinge. And before I do that, I recognize here that members A, B, C, D, and DE are not two-force members. They are multi-force members. So when multi-force members are connected, multi to multi, then I can't do anything. It's a hinge support. I represented by 2 reactions. But when I represent it as 2 reactions, dy and dx in one hinge, on one free body diagram, I reverse the directions on the other direction in the other member. So you see here dx and dy and member A, B, C, D. And in one direction, it's the same values or the same notations I applied when I consider the free body diagram of DE, but I reverse the direction. Same thing for joint E. So joint E is connecting member DE to member CE. But wait a minute, member DE is a multi-force member. It's not hinged on both ends and it's not loaded in the middle, so it's a multi-force member. But member CE is a two-force member. It's hinged on both ends, no loads in the middle, so I can represent the reactions at the hinge ends as two equal collinear reactions, which I call here FCE. So now FCE is applied, and I'm assuming here it's compressing member CE. So these two forces kind of compressing it this way. So when I assume it to be compressing CE, then joint E on member DE will I need to show there FCE, the same FCE that I showed in CE member, but FCE here is reversed in the direction when I apply it at point E on member DE, right? Same thing when you do analyze now the FCE as a reflection or a reflected force on member ABCD. So I reflected on the joint C at member ABCD. So one thing here, I have 4 members in this frame, but I will have only 2 free body diagrams to analyze because 2 force members are great, but I already used their equilibrium to figure out that I have the reactions are equal and opposite in collinear. So I cannot leverage and use their free body diagram equilibrium to solve for unknowns. It's already done. I use this information to simplify their equilibrium. So here I have 2 free body diagrams, which means I have 6 equilibrium equations. Every free body diagram gives me back 3 cards. Sum of forces in X, sum of forces in Y, and sum of moments. So I have total 6 equations here. How many unknowns I have? If you count the different now notations I have, and paying attention that I'm reversing the forces intermediate reactions at the same joint, so I'm reversing the direction, but this value is still the same. So I have here 3 unknowns. The compressive force on CE, so force FCE, and then the joint intermediate reactions of joint D, so dy and dx. So 3 unknowns, and I have 3 equations. That's amazing, right? So this means that I have a lot of flexibility in using the equilibrium equations to find the 3 unknowns I have. So the way we'll do it is we will consider both free body diagrams. You don't have to do that to figure out the 3 unknowns I do. Either one will actually give you the unknowns you're after. So, but I'm doing it just to show you as 2 possible ways. And we're lucky because the 3 unknowns are showing up, on both free body diagrams, dx, dy, and FCE. Nothing more, nothing less. So the 3 unknowns. And every free body diagram is giving me 3 equilibrium equations. So I actually can solve for these 3 unknowns using either one of the free body diagrams. So starting with the DE free body diagram here, the horizontal member, the overhang member. If I do the sum of the moments around D, I'm canceling all the moments from dx and dy. I end up with only the moment from the vertical component of FCE. All the angles of the forces here that are not orthogonal, FCE and FB, are 45 degrees. So I end up here with only the moments from the vertical reaction of vertical component of FCE and the resultant of the distributed load. So I will end up with the value of FCE to be 5.66. It's positive. So I just draw here confirming that it is the direction here, that the force here is lifting that overhang kind of roof by lifting it up. So the direction of the force here is correct as I assumed it. Then you do the sum of forces in X. You will figure out here the dx, which is the reaction of the joint D, the horizontal reaction. It's positive, so confirming the direction that I assume to be correct. And then when I do sum of forces in Y, I'll find that dy is equal to 0. Once you get that, double check, does it make sense? So in this case, it is correct. There is no actually like the vertical equilibrium here, sum of forces in Y. It's all carried out by FCE, the vertical component of FCE. No, dy is not needed. So actually I could replace the connection D here with, instead of a hinge, to be a roller, just having this overhang resting on the vertical member. Is it a good advice? No, I don't think so. It's better always to have these connections hinged. Who knows? Maybe there will be a force pushing the overhang horizontally. So I got all the unknowns using just one free body diagram. So let's try to find them using the other free body diagram that I have, which is A, B, C, D. So if I apply here, thinking about it, I have the three unknowns I have, F, C, E, and dx and dy. If I want to take the sum of the moments here to cancel as many unknowns I can, which is I will take it around sum of the moments around D. You can see here I have moment from the horizontal component of FCE. I have a moment from a horizontal component of FFB with their respective moment arms of 1 meter and 2 meters. I have the moment from the resultant of the triangular load, which is 3 kilonewton times 1 meter. And then I have the 7 kilonewton, the horizontal reaction of the support at A, and the moment arm is the whole height here, which is 3 meters. So doing the calcs, I will end up with the same value I got from the other free body diagram, 5.66 kilonewton, positive, which means that the direction is correct, I assume, but you can see here, because I'm dealing with another free body diagram, the direction is not matching with the one on the other free body diagram, which is fine. They actually should be opposite, because I'm reflecting here the force on different free body diagrams, but the value here is correct. When I do the sum of forces in X now, I will be able to find the one unknown in the X left, which is dx. It's positive, so I'm confirming here that's the direction I got. And when you do the sum of forces in Y, you will get dy here, same as we got before, dy to be equal to 0. So in summary here, we got the same answers using two different free body diagrams. Why is that? Because I had two free body diagrams giving me 6 equations total, and I have 3 unknowns. So, the problem here was set up in a way that these 3 unknowns, they exist in both these, on each one of these free body diagrams. So, and each free body diagram gives us 3 equilibrium equations, 3 unknowns, 3 equilibrium equations I'll be able to solve, regardless of which free body diagram I will analyze. So that's the end of this problem. It's just a matter of it's the same process to analyze the frames. You have to first analyze the external equilibrium equation of the frame. Try to get as much unknowns, which typically are the external support reactions. Try to get as much as you can. Take use of the 2 force members that you can recognize that are supported to the supports, are connected to the supports. Try to do as much as you can there, and then once you're out of options, now you dismember. You explode the frame, dismember, reveal the intermediate reactions at the intermediate joints, or the middle, the joints connecting the members. Take advantage of 2 force members that you recognize. Reflect the forces between the 2 force members, and try to set a plan of how to get the unknowns you have. Don't analyze all free body diagrams. We just did it here as a practice. Just analyze those that are needed to find the unknowns that you're after. Alright, so we're done here. Thanks for watching, and I will see you in other future videos. Take care of yourself and those around you.